Okay guys, in this video lesson, we're going to introduce our next unit and kind of get going on that. So what we're doing is the quantification of chemical reactions, okay? That's a pretty big fancy statement there. Really what it talks about is we're going to do all the math behind chemical reactions. That's what we're kind of getting into, okay? So we know like what gets produced and what everything is. So now it's all about how much is being produced and how much do we need. So it's all about quantifying, okay? To do that, we need to talk about things called the mole and things like stoichiometry, some big words for you guys. So let's get rolling if we can. So first thing we want to do is talk about this idea of the mole, okay? Now the mole is something that is not this furry little creature. There is a mole called a furry little creature, but it's not that in the world of chemistry. And I can go through the history behind it and what it comes from and everything, but the reality is there's actually someone who I think does a better job than me. So we're going to jump out of the presentation and we're going to go to a little TED Talk or TED Ed video here for you guys on the mole and have you guys watch that and go from there. So here you go.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
All right, so that video was by Daniel Dulick, I think it's pronounced. He does a great job of giving you kind of a conceptual understanding of what the mole is. So my job now is to take that understanding and then apply it to what we're doing in our class. So a couple of things to review. First of all, we can't count individual atoms. So we use the mole as our tool to help us bridge that world of not being able to see things into more of a macroscopic world for ours. Now, we know 1 mole is 6.022 times 10 to the 23rd particles of a substance. That's great. Okay, that's a pretty cool number. It's kind of cool to know that number if you're into science and you're a chemistry geek and all that kind of stuff. But the reality is, besides knowing what that number is, there really isn't much mathematical use for that number in our day-to-day lab stuff. Okay, so we don't usually convert in and out of that number very often. But that relationship of understanding what it means is more important to us. Okay. However, what is important to us is mass. Okay, because in the world of chemistry and science, one of the key things that we can measure really easily is how heavy something is, or its mass. Okay, so mass and volume are big ones for us, along with temperature and pressure. So if we can find the mass of something and relate mass back to the mole, then we have this link that we can actually compare mass of one thing to mass of something else and use the mole as our bridge between those two different substances. Okay, that may be kind of foggy right now. It'll make more sense as we go on here. Okay, so let's go back to this idea of mass. Okay, if we take the mass of any element on our periodic table, okay, and look at their atomic masses. So if we recall, the atomic masses earlier in the year, we called them AMUs, or atomic mass units. So the isotope carbon-12 had 12 AMUs. The isotope, oxygen-17 had 17 AMUs, or atomic mass units. Okay, so what we did is we said, well, what happens if we take carbon-12 that has 12 AMUs, and what if we use 12 grams of that? Okay, so if we had 12 grams of pure carbon-12, how many atoms would be there? Okay, so we just do a little dimensional analysis. And if you actually run the numbers, it comes out to be a very interesting number. So if you take 12 grams of carbon-12 and you convert from grams to kilograms, so 1,000 grams equals 1 kilogram, a little dimensional analysis here. And we know that 1 AMU is 1.66 times 10 to the negative 27 kilograms, because that's basically the mass of a proton or a neutron. Okay, so this is the mass of a single proton or a single neutron. So we convert from kilograms to AMUs, and then we convert, well, with carbon-12, there's 12 AMUs for every 1 atom of carbon. If you break it down, for 12 grams of carbon, you get 6.022 times 10 to the 23rd atoms. Okay, so essentially what we're saying here is for 12 grams of carbon, we get Avogadro's numbers worth of atoms, which means we get a mole. So for 12 grams of carbon, that means we have 1 mole of carbon. So 1 mole of carbon is its atomic mass. Now, because protons and neutrons are the same in any different element, so if we have 12 protons and 13 neutrons, and it doesn't really matter, that number still comes back to being the same because they all have the same mass. So now, because of this relationship, we can actually expand that idea to any element on the periodic table. So 1 mole of anything on our periodic table is equal to the atomic mass of that substance in grams. Okay? So if you go to the periodic table and we look up, let's say, aluminum. Okay, look up aluminum, and it has an atomic mass of 26.98 AMUs. We could also say it has 26.98 grams in it per mole. Okay, look up oxygen. It has 15.9994 AMUs, or 15.9994 grams per mole. So we can now start to relate mass back to moles, which is then going to be a useful tool for us. Okay. So to do that, we want to talk about molar mass and make sure that we're comfortable calculating molar masses of different substances. Okay, so when we start to relate atomic mass in grams to things, we call it the molar mass because it has to do per mole. Okay, so our molar mass is our grams of whatever we have per mole. labeled out G over MOL. This is kind of funny. This is the word, that's the abbreviation. I didn't come up with it, it's what it is, okay? So when you abbreviate mole, you can just drop the E off, okay? It's a huge savings for you. Now, when you're dealing with compounds, we need to take and add them all up, okay? So it's really easy to find the molar mass of a single element because that's just its atomic mass. But if you have a bigger compound, you need to be able to add them all up, okay? So we're going to do a little practice problem now on the board, okay? So we know that the molar mass is grams per mole. And we want to add up all the atomic masses for whatever compound we're working with. So let's go to sodium carbonate, and let's work that one out together, okay? So sodium carbonate, first thing we want to know is its formula, and then we want to have our masses. So you're going to need your periodic tables with you to do this. So sodium carbonate has a formula of NaCO3. This is a 2 minus charge, it's a 1 plus. So I need 2 sodiums here, okay? So I have sodium, and I have 2 of them. I have carbon, and there's 1 of them, and I have oxygen, and there's 3 of them. Okay, so here's how many I have. I'm going to multiply those by their atomic masses. Okay, so if you look up sodium, sodium has atomic mass of 22.99 grams per mole. Carbon has a mass of 12.01 grams per mole. These are the atomic masses off our periodic table. Oxygen has atomic mass of 15.9994 grams per mole. Now here's a problem I run into. Different periodic tables sometimes will round this off differently. So if I'm using a table from an internet source and somebody else is using the book's periodic table or somebody else is using a periodic table that I gave you, we have all these different numbers. So what I always tell my students is, and what I always do, is I take every number I'm working with in this and I round it off to the hundredths place. Not because the hundredths place is special, but because I have found that if those different sources that I've looked at over the past years, they always are the same if I round them back to the hundredths place. So I have less discrepancies in my numbers. So that's what I do. So instead of writing this out, I'm going to always write it as 16.00 grams per mole. Plus, that makes it a nice even number for me to work with. Okay. Now I'm going to multiply and then add them up. So 2 times 22.99 is 45.98 grams per mole. 1 times 12.01 is still 12.01 grams per mole. And 3 times 16 is 48 grams per mole. Take all these things, add them up, and that would be our molar mass of sodium carbonate. Okay, so 45.98 plus 12.01 plus 48, and I get a total of 105.99 grams per mole. Okay. So the molar mass of sodium carbonate is this number. Okay. This is a key number for us. Anytime we do any work, any stoichiometry, any mathematical stuff in chemistry for the next 2 weeks, we're going to have to solve for molar masses because it's our link between moles and grams of a substance. Okay, it becomes one of our most important calculations through the entire year is to be able to do this one step right here. Okay, it gets to be such a thing that we do so often actually that by the end of the year you won't even think about doing a molar mass. It's just be part of your process. So it'll be like, oh, do the molar mass quick and then use that number for something else. Okay, so we did one practice problem. There are 2 more here, lead 2 nitrate and bromine. You can do those on your own and try those out. But we're going to end the video lesson here, and then we'll come back tomorrow and we'll take a little bit more look at this. Thanks, guys.